about Taylor series. We reviewed some material regarding Taylor series in the beginning of the course. So now let's talk about Taylor series for functions of complex variables. So here is the main theorem we will be discussing today. So suppose that a function f of z is analytic throughout an open disk. So here's the disk. The disk is centered at point z sub 0 and radius of the disk is r sub 0. So let's look at this disk and look at the point z inside this disk. Then at each point z in that disk, f of z has the series representation. And here you see familiar formula for Taylor series. An is a coefficient, and this is a power series, z minus d sub 0, centered at d sub 0, to the power n. And the coefficients also the same as you seen in calculus, and derivative of function f evaluated at point z sub 0. Of course, we know that our function is analytic, so according to generalization of Cauchy's integral formula, we know that we will be able to compute all the derivatives. They will be analytic functions. And also now we have an extra formula, again due to generalization of Cauchy integral formula, we can compute our coefficients not only just differentiating our function, but also we can write them as integrals of this form where CR is some contour that is inside this disk. And obviously n here is an integer, positive integer, or non-negative integer, 0, 1, 2, 3, and so on. So a couple of comments about this theorem. Of course, if we write that our function has Taylor series representation, it means that this series converges to our function f of z, right? So if we look from right to left, this series converges to our function f of z if z is inside this disk. And next comment, if we look at any closed subdisk, so let's say, so this is our r sub 0, let's look at the smaller radius r and look at the closed subdisk, right? So then our series would be convergent uniformly. So what does it mean uniformly? So then how did we define convergence? To define convergence of a series, we said that we want to look at the sequence of partial sums. And then we were defining sequence of partial sums. How do we define convergence of a sequence? To define convergence of a sequence, we say that for any positive number epsilon exists such n, starting from which all of the members of our sequence belongs to a certain disk, right, of radius epsilon, centered at the point where the limit of the sequence is. And now our series depends on z. So if it is possible to find such an epsilon for all z, so the same epsilon for all z, then our sequence would be convergent uniformly, and therefore if our sequence of partial sums converges uniformly, the series is called uniformly convergent. We'll look at an example in a second. And then the third comment, there is a special case, as you know, when z sub 0 is 0, then we have a Maclaurin series. So for Maclaurin series, of course, this formula will look like, if I write here Maclaurin, then formula for f of z would be f nth derivative evaluated at 0 divided by n factorial, and here would be z to the nth, and I forgot the sum, and runs from 0 to infinity. Maclaurin series. And in the beginning of the class we discussed some examples when we were talking about Euler's formula. Say if we have function e to the z, then it's easy to compute all of the derivatives. They will be still e to the z. If we evaluate each derivative at 0, we will get 1. So the formula would be 1 plus z squared over 2 factorial. So here obviously we have over 0 factorial, which is 1, over 1 factorial, which is 1, plus z cubed over 3 factorial, and so on, z to the nth over n factorial, and it will continue. And related to this formula, we also discussed, by the way, where this series converges. So what is the radius of this disk R sub 0? We know that our function e to the z is entire function, so it would be good for all z less than infinity. And we can look at cosine z and sine z, and we know that cosine is an even function, so you can honestly compute all of the derivatives. I believe you remember that we wrote this expression, so it will be 1 minus z squared over 2 plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and so on. And sine is an odd function, so we start with z minus z cubed over 3 factorial plus z to the 5th over 5 factorial plus or minus z to the 7 over 7 factorial. And both series for cosine and sine, they are both entire functions, so the series also converge for all, both series converge for all z less, modulus of z less than infinity converge everywhere. So let's look at another example. So it's example 2. If we want to write a Maclaurin series for the function 1 over 1 minus z. If you look at this function, obviously when z equals 1, we will have function is not defined, it has singularities. So if we look at our theorem, function would be analytic if we take our z in the unit disk. So z, modulus of z less than 1. Then our function would be analytic. Then we can honestly compute all of the derivatives. So derivative of 1 minus z with respect to z would be, so we have here 1 minus z to the negative 1, it will be 1 minus z to the negative 2, and we have to multiply it by minus, and also using the chain rule we have to multiply by another minus, so it will be this, and we can continue this process. We can see that if this is our f of z, then f of z nth derivative would be, then next would be, we will have negative 2 times, and so we will have n factorial 1 minus z to the power n plus 1. So this would be all of our derivatives, and then if we evaluate this derivative at the point z equal 0, then we will end up with just n factorial. And then our formula for coefficients is derivative over n factorial, so n factorial over n factorial will be cancelled, and as a result we will have the following expansion: 1 over 1 minus z would be 1 plus z squared plus z cubed plus. So you have probably recognized here geometric series that we discussed in the last lecture. So, and we know that this series converges when modulus of z less than 1. Okay, so here we can write that 1 over 1 minus z equals to sum n from 0 to infinity, and what we had, n factorial over n factorial, z to the nth, and this I cancelled, so we have sum n from 0 to infinity, z to the power n. So this is geometric series, it converges. So now let's discuss its uniform convergence. So then let's look at the example number 3, and let's show that the series sum, say n from 0 to infinity, z to the n, uniformly convergent is uniformly convergent in every closed disk, in every closed disk, when z less or equal than r and r is less than 1. So, so how are we going to show this? So we take epsilon, right? As we said, that we have to deal with sequence, or when we try to prove uniform convergence, we talk about partial sums. We can take the sequence, and if you remember, we were talking also about remainders, right? So we know that if series converges, it means that sequence of its partial sum as n converges to a certain number, say s, and s is the sum of the series. But alternatively, we can look at the remainders. If we subtract from s partial sums, and then we will end up with a remainder, and this remainder for that chosen epsilon must go to 0. So let's write down the remainder. The remainder. So how we write it? We take our function 1 over 1 minus z and subtract the nth partial sum. So we will subtract 1 plus z squared plus z cubed plus z to the n. So if we subtract this, what we will end up? So here we have similar expression, just infinite. So when we will be subtracting after we subtract, so here we'll have this expression, infinite expression. So the first terms will be cancelled, and we will end up only with the term starting with z to the n plus 1 plus z to the n plus 2 plus z to the n plus 3 and so on. And then we can pull out z to the n plus 1, and here it will be 1 plus z squared plus z cubed. And we obviously can find a sum, so then this would be equal to I'm continuing here, that our remainder would be equal to, we know that this is 1 over 1 minus z, so we will have z n plus 1 over 1 minus z. So we will get this expression. And then let's try to evaluate this. So if we want to evaluate this, or estimate this, it would be better to say, our goal is to show that this is less than epsilon. So if we're taking z is any number, so here is our unit disk, let's radius 1. So r is less than 1, so here will be our disk, closed disk, including the boundary of radius r, so this is our disk. And if we are talking about modulus of z, of course the biggest possible would be r, right, when we're sitting on the boundary. So that would be less or equal to the r n plus 1, and here we can write 1 minus r, right? So that this r will fit all of the possible z inside this disk. And because modulus of z is less than r. And we know that r is also less or equal to r, and r is less than 1. If we have a number which is less than 1, and we will be raising it to a big power, our number will be decreasing. So since our number would be decreasing, so for any epsilon, for any positive epsilon, we will be able to find such an n, starting from which all of so this number is within this disk with radius epsilon, so this number will be going to 0. This finishes the proof. In other words, the remainder may be made as small as we wish. Now let's sketch the proof of this theorem. So what do we want to establish? So we want to show, we want to have all of our derivation based on Cauchy integral formula, because we have proven Cauchy integral formula, which is f of z equals 1 over 2 pi I integral c r and f of s ds s minus z. So what is CR? So now let's make a picture. So first we have this disk centered at z sub 0, and radius of this disk is r0. And then we have a disk, a small circle with radius r, and that would be our contour CR. So every traced in a positive direction. So that would be one thing that we will be using, and also another thing that we will be using to sketch the proof is geometric series. And we know geometric series that 1 plus z squared converges to 1 over 1 minus z. We will be using that. And from here we want to show connection to the formula that f of z equals to f at z sub 0 plus first derivative at z sub 0, z minus z sub 0 plus second derivative at z sub 0 over 2, z minus z sub 0 squared plus third derivative at z sub 0 over 3 factorial, z minus z sub 0 cubed, and so on. Okay, so now let's look at point z sub 0. So here is our point z sub 0. And what can we say about z? So point z here is somewhere inside this small disk. And what is s that is also involved? S lives on the boundary here, s. And now let's see, if we compare two distances, distance between, so z sub 0 is this point, right? It's this point. So z minus z sub 0 and s minus z sub 0. So which distance is bigger? Obviously the second one. So we have this sign. And then let's divide both sides by this. So we will get that z minus z sub 0 over s minus z sub 0 is less than 1. That's what we have. So now let's look in the integrand of here. So here we have expression of the form 1, let's ignore f of s so far, 1 over s minus z, right? We have this function in the integral, in the integrand, inside our integral. So now let's rewrite this function in this form. I will factor out s minus z sub 0, right? And then I will write times 1, and here will be 1 minus z sub 0 over s minus z sub 0. Let's check what happens if we distribute it back, right? If we multiply, we will have here s minus z sub 0. This would be cancelled, so we'll have s minus z sub 0 minus z and plus z sub 0. Z sub 0 would be cancelled, and we will have exactly the same s minus z. So this is exactly the same expression as we had before. So why did we do this? Because now if we leave this alone for a moment, right, and look at this expression, we see that we have 1 over 1 minus, and modulus of this thing, we know from here that modulus of this thing is less than 1. So we can look at this expression as a sum of geometric series. So we can rewrite this as a geometric series, which means that that would be 1 plus z minus z sub 0 over s minus z sub 0 plus z minus z sub 0 over s minus z sub 0 squared plus z minus z sub 0 over s minus z sub 0 cubed, and so on. And so what are we going to do next? Next, we're going to multiply this back to each of the expressions. So then we will have 1 over s minus z sub 0 plus z minus z sub 0 s minus z sub 0 squared plus z minus z sub 0 squared s minus z sub 0 cubed, and so on. So this is our expression. So what are we planning to do next? Next we will multiply this by f of s and 1 over 2 pi I and integrate each, and integrate it term by term. We know that this is uniformly convergent series, so we will be allowed to integrate it term by term. So let's add just nth term. So general term would be z minus z sub 0 to the power n divided by s minus z sub 0 to the power n plus 1. So what we will be multiplying? So here is the beginning of our formula, here is the end. I will copy this on this board. So what we have is we have s 1 over s minus z equals to 1 over s minus z sub 0 plus z minus z sub 0 over s minus z sub 0 squared plus z minus z sub 0 squared s minus z sub 0 cubed, and the nth term z minus z sub 0 to the n over z minus z sub 0 to the n plus 1, and so on. So then we will multiply everything by f of s 1 over 2 pi I f of s, and then we will integrate along the contour CR. So what do we have here? Here we will have 1 over 2 pi I integral f of s minus z ds CR equals 1 over 2 pi I integral along CR f of s ds s minus z sub 0 plus 1 over 2 pi I CR. Now I can erase this. CR f of s ds s minus z sub 0 squared z minus z sub 0, and we will continue 1 over 2 pi I. Maybe I should write the second term as well, and then the general one CR, and then it will be f of s ds s minus z sub 0 squared cubed, sorry, so So then v cubed z minus z sub 0 squared 1 over 2 pi I, then plus 1 over 2 pi I integral CR f of s ds over, oh sorry, here I had to write here s minus z sub 0 to the n plus 1 z minus z sub 0 to the n. And now let's look, what do we have? So if you look at this part, right, then according to Cauchy's integral formula, we will have the just f of z. So this is f of z. So we have f of z in the left hand side. So let's see what do we have in the right hand side. In the right hand side, first term would be obviously f, according to Cauchy's formula, f at z sub 0. And then if we look at this expression, that would be just first derivative, right? So that would be first derivative. So here it's 1 factorial will not play. So that would be f prime evaluated at z sub 0 times z minus z sub 0. And if we look further, if we look at the nth coefficient, that would be just fn evaluated. So this coefficient is fn and derivative evaluated here divided by n factorial, because otherwise according to Cauchy's formula we have to keep n factorial on top. But here we don't have this n factorial, so it will be already divided. So we will have f nth derivative at z sub 0 over n factorial z minus z sub 0 to the power n. So this is Taylor series, and this finishes the sketch of our proof. Thank you.